F1 season is about to start, I think it's fitting that we create racetracks using maths, or also known as procedural generation. As you can see over here, when I press this button, a different type of layout of track is generated. I'm going to show you how you can do that. Get into it. So I was originally inspired by this video, which is using AI to create F1 tracks. And I thought, this is kind of cool, and that the way it takes all the AI top-down images and then uses Stable Diffusion to then create a new image based on that. I thought it was kind of cool, and I wanted to give my go, I guess, except not use AI and use more traditional methods using algorithms essentially, because AI is great, but it's very inefficient and it can have flaws. But with our own type of algorithm, we can really fine-tune it for ourselves. There are many ways to generate a racetrack, and there are a few, and there's no correct way to do it. You do whichever way suits your needs. This one is from an actual game, and they have like this procedural custom engine, so a proprietary engine for their game. And the way they did it is actually use a Voronoi diagram to then generate a racetrack, one that's very familiar to an F1 track because it is like an F1 sim game, and you can see. And then this is the output results. Unfortunately, the game is not reviewed very well, but I still thought it was kind of interesting either way for Racecraft eSport if you want to check it out. And another more different method is using convex cells and then interpolating the points of the convex cells. And so we can see here, we generate a set of random points. We go and create a convex cell. If you know what a convex cell is, what they call like a GIF wrap. So there's a bunch of points, and then you sit them together and you find the points that connect to each other essentially. And then you essentially just interpolate the points. So to add curve edges, in this case they find like a midpoint and they like displace it from the center to add curves. And I'm going to use this kind of method. I'm going to use convex cells. I quite like this method. And the Voronoi diagram is definitely an interesting take as well, but I want to go for what I would consider a bit of a simpler approach. So the language I'll be using is Python, because it's easy. The Pythonic way is very easy and simple to understand. So hopefully you should be able to translate this to your own language, if so, or game engine. And to represent it 3D, we're going to be using Raylib here, or the binding for Raylib in Python. And this current scene is always simply doing is creating a window, so this window, and then setting a camera just with a 20 zoom in, and then just having the background black. So if I run this, you should be able to see. So I run this Python main.py. There you go. All it is a black screen. So that's all it is at the moment. So let's begin. Okay then, I've updated it. I made a new class to organize our code called create track that we're just importing in, and at the moment it's just this. So we just have a function called create track, which we want to pass in the height and width of essentially our racetrack, so the maximum possible X value and Y value you can go to. And we just simply generate a uniform distribution of random points. So anything from 0 to 100, in this case, if I pass through 100, and I want 10 of them. So it's going to be an array of 10 points that are randomly generated, both for the X and Y. I'm using NumPy for this, and then stack them so it becomes like a 2D array. So X, Y, X, Y, X, Y. And I'm not going to implement my own convex cell. There is plenty of tutorials out there, and this video would get extra long if we have to go through that, and interpolating as well, which is basic case, which we'll get to later. So I just used their convex cell, which requires a 2D NumPy array, and it will create the whole, so it makes it easy for us. And then we get the vertices from that, and then we put it in its own array, and we return that. So when I just return this or run this, you can see we have ourselves a nice racetrack. And if I run it again, it should be randomized each time. There you go. Now I think the next step would be to curve the edges so we get a nice rounded track. And we got it's going to get a bit more complex now, because we're going to use some interpolation. And within our create track class, I've added a new function called curved corners. Very cool name. And we just need to pass through the points, so our whole vertices that we have so far. And we also have this embedded function, which we'll come to later. But we have what's our inner point and outer point, and that's hard to explain, so I'm going to just show you by drawing it. So let's say this is our array of points. So we have our X and Y, 0, 2, and they're in a linear, they're just in a flat array. So they just go, when we loop through, we obviously go 1 by 1 by 1. And so if we want to get a corner, we need to know we have to then create points in between these. And in this case, I'm using this package called just Bezier.py on GitHub. It's completely GPL license free to use, and it's just a single file you have to add. And so if we look at their examples here, you can see that to curve it, the more points you have, it curves between them, and it connects between the 2 points. So if we go back to our little Inkscape example, we have to imagine that when we have our 2 points, so if I draw a line here, and we've got our 1 point here and 1 point here, in order to, when we leap through the row, we go 1 and then 2. So how are we going to curve them? We will have to look behind us and look in front. So for example, when we're on this point, we need to get the previous, we have to look back a point to know where the previous point is. So like this, and then add a point between here, and then look in front and point between here. And so the code kind of looks odd, but in this case, what I'm going to do is I will add a point first here, so close to the original point, and then apply a point that's further away, so it's actually close to this point. And so when we do the full loop of convex holes like this, for example, eventually, we then add this one, we then add this one, here's the next point, so then we add this one, and then we add this one, and then we add this one, and what we actually have is then we can then apply a Bezier curve to each of these points, like so, and then they should curve like this, and they'll curve something like around about that. So as you see, we loop for the array, we get a random percentage. So for the closer to the array, the point that's closest to the original point, we're just going it from 0.1 to 0.4, so 10% to 4%, 40% to the distance from that and the next point. And then we calculate this custom point, which is, just up here, which all we're doing is we're interpolating. So we're finding the X and Y position between those points based on its percentage. So in this case, 0.1 between 4 for the X and Y. And then we append that to what we call, or what I'm calling inner point. Kind of hard to explain, but the point that is closest to the original first point, the first convex hole point. And then the second one is going to go into the outer point, so the one that's closest to the upcoming next point. I hope you understand this is quite hard to explain. And we just MP array, just so rather than it being a weird list, that's just a little thing. Now we apply the Bezier curve, and the way we do this, we have our t values, and the way a curve is actually made, it's just a bunch of points along that curve, and so when we join them together, it looks curved. So the more points we have, the smoother the curve, but at the cost of more memory and of course processing power to do it. And I'm just going to do 10, which is quite small, but it should be fine. And all it is a bunch of arrays that contain like a value of 1. That's it for now, like a temporary value. And all we are is going through the points. Now I do check if I equals 0, and I'm just checking the first element array, and this is because when we're applying our points, we want to apply the last point from the previous one, because this is the first element. We can't go, apply the curve to the previous point, because that does not exist. We have to get the last point again, because that's the one that will be behind it. Kind of explain. And that's the only if case we do, and then besides that, we just apply it as normally. So you see here, we give the Bezier the curve its t values, so how many points it wants to do, and then we get our outer point, so our point that was furthest from the original point, but in this case it can be closer to this point, and then it's an inner point, and then we apply those curves to it, and we also append the last point in. So that's when we run this. If you remember before, we had a massive gap in, and that's because we need to join them. When we join them, we're just adding the first point again at the end of the array, so that means it will create what looks like a full circle, a full convex hole. So nice, and all I'm doing is just returning the new array. And if I just run this now, boom, and if I move my head out of the way, you can see I can just move this as well. You can see here that we have a nice smooth racetrack, and if I can just keep running it, and it'll be randomized each time, you see. But if I keep running this, you notice the shape is kind of similar. They're just kind of almost like squash circles or kind of triangles. They're really very consistent. They're not actually as random as you might think. So there's ways we can do to improve this and mitigate this issue. First issue we can do is we can just change the height or width of our thing. So when we run this, you notice we get a lot more squashed convex holes because the height is a lot smaller, so in this case half, and then we can actually take it even further, go to 20, but this can remove kind of undesired results. You can see the track is very small now, but you get these very long ovals, and really it's still the same issues as we get before. It's just that now it's squashed, so really they're the same shape but just kind of squashed instead, so it doesn't really solve our issue. A really simple solution: just add a new point. We have our convex hull, so that means we can just apply a new point between 2 points and displace it by a random amount, so have it closer to the center or further away from center, and we can add them as many times as we want. We can also check the distance between them, so only choose very long tracks to add it, or even very short tracks to add a lot of curves, kind of like a chicane. Let's just go through it again and pass it through the points. We find the center between all the points, so kind of the area, the center, and this is because we want to displace it, so interpolate it between either move away from the center or close to the center. And in this case, we just get the index from the array when we get our random kind of point and get the midpoints. All it is we're dividing by 2, so we can actually find a different value by doing, let's say I only want like a third of the length, for example, but we're just going to go half in this case, easiest. So that's already simple math, get the point divided by 2, that's your halfway point. And we'll add a scale factor, how far we want to displace it. So in this case, just generating it from 0.1, 1 from 0.1. So either 1 would be don't move at all, stay where you are, or 0.1 would be to move a lot. You could, depending on how you do it, negative or positive, it would be move away or against. And so we just get it displaced, get the center, combine it with the scale factor, and then we just times it with all the values, so the x and the y, and simply this will just give us that new x and y position that's been displaced, and we just insert it in. So we just get the index where we want, so between the 2 points, and we add a +1 because we're comparing it to the original, so we want to add it next. Otherwise what we do is we're checking between the wrong points, and we just return that. And so when I run this, hopefully we should have, there you go, a little dip in our thing, in our little track. And if we run it again, we'll get it random each time. You can see this doesn't look too great. It's not perfect because we need to add perhaps more random points between our points, and you may see less effective. So this wasn't too bad. Python, this one, see, yeah, a little bit more oval shaped again. Go for one more time. And that was quite a cool track here. If I move it slightly to the right on OBS, so you see there, kind of cool, hey? So I slightly updated it. This time add unique values. So use the package random and get a sample of between 1 and the length of the points, and 3 of them. And we just loop through it instead, and then so it's the same thing, but instead we're adding unique ones. And if we add it, we'll get crazier results like this. Like, ooh, now we're getting some interesting results. And again, okay, not too bad. It's kind of still more sane. Advent. Oh, look at this one. Imagine an F1 driver right now doing a sharp turn and whatnot. You see, we still get some undesired results. It does require a lot of fine tuning. This one, no, that's kind of crazy. I'll go one more, and this one even generated off the. You can. For some reason, it didn't generate. So there we go. Kind of cool. So we're getting very interesting ones. Not very F1 track like, but still a track nonetheless. Let's take this to the next level by going into 3D. Yes, it's actually really easy. It might seem very complex, but we essentially just do the same procedure of create our track, but then what we just want to do is apply a Z value to it. Now, if your map's just going to be straight up flat, you don't actually need to do anything. You can just set it to 0 or whatever you have the default flat plane as, 1, 2, whatever. But to make it a little bit more fun, we're going to generate a Perlin noise here. And I'm just using the Perlin noise package, and we just pass it our seed. So this is just so we can have some uniform, so the user can set the seed and you just know what the track number is. For example, the octaves, the size of this Perlin noise, so 100 by 100. If you have it bigger, it's going to take a long time to process. You want it quite small, and then just scale it up. That's why when we had the camera zoomed in on the 2D map by 20, because if we try and fill it up to 3000, think of how many points that is. A lot of points to generate, so keep it small. And we just go through each X and Y in the range, and then that will give us the values for each point. Now, I'm also doing it by 10, so multiplying that value, because height maps just usually return a value from -1 to 1, and you're not going to see a visible effect in 3D when the z-axis. So I'm just basically multiplying that 10 so we can see a bigger visual difference. And the more you do it, the more exaggerated that Perlin noise is. Alongside the octaves will determine how many like bumps and hills there are. So less, you're going to get more like bigger gradual hills. With more, you're going to get a lot more mini hills with a lot of peaks. And I'm passing through a track 3D, and that's so I can just swap between 2D and 3D. And all it is, so we just loop through, and we have to reorganize our X and Y a bit. The way Raylib interprets X, Y, Z is the Z would be the Y axis in something like Blender, and so we have to swap them around. So this time the Y axis is the generate Perlin noise, so we're just swapping them around and inserting them. So you can see X, Y, and then Z. So our original Y axis in the 2D is now our Z axis, and we just simply add this to our curve array. We'll return it in our curve array, and in our main I'm just using argument parser, so the user can type the command like, oh, it's either 0 or 1 to determine if it's 3D or not. And so now you see we have the 3, and we just also pass it in, and we just check if it's 0, do it 2D like our usual way. If it's not, we just generate it in 3D. And in Raylib it's super easy. You just now do a camera 3D, and you begin a 3D scene rather than a 2D scene. And I have a nice little camera orbiting the track, which will be cool to watch. And I'm also decided now to add the draw the text of the seed. We can see the seed, so what the level seed is. Like, you know, in Minecraft you have that unique seed when you press F3. It's just like that. And it's just exactly the same as 2D, but we're just using cylinders in this case to generate a 3D structure. Now, when I run this, it might look a bit odd, and that's because we haven't got any shading, and you actually have to use OpenGL shading, which is like a whole different video itself. So everything will look like Fulbright. So if I run this now, there's our track in 3 dimensionals. Pretty cool. And there are curves. You can see it kind of a bit in some of these sections. It might seem a bit hard though, but we can make it more obvious by, like I said, going to our noise section and doing 20, and we should see a far more dramatic effect now. I run it. There we go. A little bit more. You see that one's way high now. And if we up the octave, so go back down, let's say we want 6 octaves in our thing, we got a very bumpy track. Would be crazy to drive on. So that's it. That's our racetrack that we generate is now in 3D. It's really that simple, and so it really wasn't that complex. And because we're just getting out the raw coordinates, it means that it's very easy to port this into other languages and even other game engines, because rather than me showing like, oh look, this is how you do it in this specific game engine, it's like, oh, it's not once I'm using this game engine, and so I'm trying to make it as like pseudocode as possible. So how does it differ to this one that we first looked at in the start? Well, they essentially just interpolate between all points, which is why theirs is way more curved, and in fact why they also have these little circles in, which you definitely wouldn't see in an F1 track, which would cause crashes at like 200 miles per hour. But this is what theirs is different. So it's just slightly different, and there's some studies as well out there if you want to look at that do interpret and how they do procedural racetracks or endless racetracks, for example, so the player keeps driving and it'll keep generating new points. There are a few GitHub repositories. For example, this one is on GitHub, so you can actually view the code if you want. As if we scroll down here, code can be found here, and they use Pygame to render theirs, and you can just run it with, again, simply with a Python script, which is very cool. So what are we kind of lacking with this? Well, you can see the results are very randomized. I know it's kind of weird, procedural generation random, but with procedural generation, you want it to be consistently random and it's entertaining. So there's like, let's say if I wanted to generate a F1 track and in that style, I would need some consistency. For example, this is going to be probably a terrible F1 track. Where do they start? You got to think of like how long you need a stretch that's going to be long enough for the races to appear. And with all these goofy corners as well, probably not exactly the most fun track to go on. But this just gives you the general idea of how you would create a procedural generation, and how you can just easily manipulate it by just adding new points, changing points, displacing points, and of course interpolating between points to add curve edges. And it's surprising how few games actually do use procedural racetrack generation. A really cool example, I think not many people really know, is F-Zero X. If you unlock the X Cup, which you had to beat every other cup in massive difficulty, was all the next tracks were procedurally generated, and this was on the N64. And I think something like this is kind of amazing to have, and pretty cool. In fact, it was flawed as well, and apparently some would generate incredibly sharp turns, resulting in all the AI just flying off because they couldn't handle it traveling at like 1,000 kilometers. This, I think, is a really cool use of it. It's a shame that F-Zero GX didn't have that, but it has a lot of potential to create very interesting results and a lot of replayability. For example, F-Zero X is a Grand Prix game, so you have to go through 5 tracks and obviously perform well in it, so place near the top in order to win. And I think in a game like that would add good replayability if the players are rewarded with some XP, whatnot. And in multiplayer, kind of like almost like a roguelike, really. You don't know what you're gonna get next. And so, what did you think of that track? And are you hyped for the F1 season? What games are you think are lacking in racing games? Particularly, I think at the moment they kind of lack replayability. And if you want to run my code, then I've put it on GitHub for you to look at and investigate yourself. It's under MIT license, so do whatever the hell you want with it. And have you attempted any procedural racetracks in your time? And what do you think of it? Do you prefer handcrafted tracks, or would you like a bit of mixture of both? Have some nice handcraft tracks while also adding a randomized game mode as well to add replayability. And would you like to see more kind of procedural racetracks in the future in video games? It seems like they just now present you with an open world map and create racetracks based on that. So anyway, see ya and have a good one.